Now, today's topic is a little bit familiar to a lot of people. It's kind of a review of physics. And so we're going to be talking about some physics applications of integration. And remember, when we talk about applications of integration, it's always about what's the total. So we're trying to measure something. And we're going to start with mass. So we're going to ask, what's the total mass? So our setup is we have a density function, which we usually use delta for density. And it says, how much material is there at a given location. Now, we might have a density function which is two-dimensional, and that's if we have a two-dimensional region which we're trying to talk about. Sometimes you'll see this referred to as a lamina, which is just a fancy way of saying a flat thing, a flat two-dimensional shape. Or we might have a density over a three-dimensional region, which can look like, well, just about anything that's three-dimensional. And so the density says how much mass is there at a particular location. And now the question is, well, how do we find the total mass? Well, the idea, as with all integral problems, is to say, let's break things into small pieces, understand the small pieces, and we put them back together. So when I break things into my small parts, so if I'm in two dimensions, my small parts have these little bits of area. So think of it as my delta A. So that's my little bit of area. And I say, well, how do I find the mass that corresponds to that part? Well, the density, if you look back at the units, it's mass per your area. So to find the density of my little piece, I take the density of that piece times the size of that piece. So this part right here is the mass of a little tiny piece. Or more appropriately, we should say, it's approximately the mass of a little tiny piece. The problem is that our piece is small, but the density might still vary a little bit within that, but it won't vary by much. And that's the important thing, that the mass will not be far off. And now we add all our pieces back together, and that gives us a really good estimate for the mass. Of course, we do what we always do and say, okay, smaller and smaller pieces. What happens? And the answer is that we go to the right answer. And so to find the mass, the moral is integrate over your region density dA. Now again, that's the two-dimensional setting. Well, what if you want to go to three dimensions? And not much changes. It's the same idea. So we're going to sort of skip the intermediate steps and say, what happens? Well, we break things into little pieces. So now that's like the dV. The dV being a little tiny piece. Multiply that little tiny bit of volume by the density there, and that gives you your little bit of mass at that location, and then you add it up. So whenever you see an integral sign, you should really say, this is a shorthand notation for summation. So we're adding up lots of little pieces of mass. So let's start with an example. Find the mass for the following region. Y squared is less than or equal to x, and that's less than or equal to 1. And the density is x times y squared. All right, well, we can sketch our region. That's often helpful. So we have a few curves. X equals 1. That's a pretty easy curve to sketch, just where all the x values are 1. What does x equal y squared look like? Yeah, it's a parabola, and it's turned sideways. So y equals x squared is a parabola we're normally used to drawing. It opens up. X equals y squared is a parabola turned on its side. All right, so it looks something like that. And so if I want to have x be greater than or equal to y squared, I want it to be to the right of y squared. So I want to be in that part of the parabola. Of course, x less than or equal to 1 means I want to be left of 1. And where do they overlap? Well, in this nice, convenient shape here. All right, so here we go. There's our shape. All right, hardly looks like I did any shading at all, but there's some green there. Okay. Well, now what do? Well, we apply the formula. We say that mass is going to be the integral over our region R of our density xy squared dA. So here's our density function. Now, what's the next thing we need to do? We're going to work towards bounds, and if we're going to have bounds, we also have to make a choice. Should we integrate dx dy or dy dx? Which comes down to, is this a problem where it's easier to integrate horizontally or vertically? Horizontal seems pretty natural for this problem, especially because given our curves are expressed in terms of x equals x equals. So we're going to work on doing a horizontal integral. Well, horizontal integral means that my inner curves are from x equals to x equals, so that's a dx dy integral. I can tell because the dx there tells me that goes with an x equals. The dy here tells me that goes with y equals. All right, with the bounds now. Well, we have to figure some stuff out. One thing we have to figure out is where do we intersect? So in other words, where does y squared equal 1? What is it? Yeah, -1 and +1, plus or minus 1. So -1 below, +1 above. So what are my outer bounds? -1 to 1. Now I go to my inner bounds, and these are my curves. So I want to go from x equals something to x equals something. Well, I say, what's on the left? That's the low value. The left is y squared. So I go from x equals y squared to the right, which is to 1. X equals 1. Okay, so now we have our bounds. We have our integral, and we work through it. -1 to 1. Integrate with respect to x. What do you get? 1/2 x squared. The y squared is a constant, stays as y squared. And I'm evaluating from x equals y squared to x equals 1 dy. We evaluate, -1 to 1. We'll have 1/2 y squared, when I plug in x equals 1, minus 1/2 y squared squared times y squared. It's a lot of y squareds. Put them all together, y to the 6. Okay, dy. What's the integral of 1/2 y squared minus 1/2 y to the 6? So 1/6, yeah, y to the 6, minus, sorry, y cubed, sorry. I'm so used to writing 6 and 6 there. Thank you for pointing that out. Next one. 1/14, we'll make the same mistake again, y to the 7th. And we evaluate from -1 to +1. And that's 1/6 minus 1/14. Subtract and plug a negative. It'll be -1/6. And then it'll be plus 1/14. Well, 1/6 minus 1/6. It'll become 1/6 plus the 6, which is 2/6, or 1/3. Minus 1/14, minus another 1/14, minus 2/14, minus 1/7. So this becomes 7 minus 3/21, which would be 4/21. All right. Now, you might ask the question, 4/21 what? Well, the answer is, we didn't say. If we had given you units, you'd give units here. But for now, 4/21. 4/21 somethings. Whatever your most convenient unit for mass is. Now, you might think, this feels a lot like what we did previously. So in the last semester, when we did Calc 2, we said, you know, we did these problems where we found mass of a region. what's different? Well, previously, when we did these problems, we said, look, mass can only depend on one variable. It could depend only on x, or it could depend only on y. Now, our big thing, our new shiny improvement, mass can depend on both x and y. So that's what's different. The good news is that's a fairly small change, so not too long for us to figure it out. Okay. Well, after we do mass, what comes next?
Center of mass.
Center of mass. Yeah, we're going to build up to that. But first, let's take a moment and talk about something else. So, we're going to head towards center of mass, but first we need to talk about what we have our moments. So, what's a moment? Well, a moment is measuring in some sense a turning effect, and that's about as detailed as I can go. If you want more, you can take physics, and they will probably try to say more. It won't really add anything, but how do you find moments? Well, what you do is you combine two ideas. You combine mass and distance. So that's what a moment is. You multiply mass times distance. Now, of course, the question is, once you talk about distance, distance to what? Because I can talk about distance to many things, and it depends where my setting is. It might be to a point, it might be to a line, it might be to a plane. It all depends on context. So when we talk about moments, it's never just find the moment, it's find the moment with respect to something. And so that's the key. Always remember that moments are with respect to something. Also, I'm going to be a little bit cautious here and say, when I talk about the word distance, it feels like I should have always a positive measurement. We allow for negative distances. In other words, a better thing would be a location. So how do we do this? Well, we do the same thing that we did last time when we talked about mass. I said, when I was trying to find mass, what did I do is I broke things into little tiny pieces, density times the little bit of area or the little bit of volume. It's the same idea. So I'm still breaking things into little tiny pieces. I still have density times my little bit of area. I'm thinking of two dimensions right now. So I have the mass of my little piece, and then I multiply it by my distance formula. Now, of course, the distance formula depends on the context, and now I add things up. So in other words, when I want to find the moment of some large structure, I break my large structure into little pieces, find the moments of each piece, and I add them all together. So we have that the formula for a moment, it's the integral over your region, your distance function, times your density function, times your little bit of thing, your dA, or if you're in 3 dimensions, your dV. All right. Now this is the formula I encourage you to memorize, because it's very simple to remember just one general framework and then adapt it. So let's talk about some cases. I've drawn here a 2-dimensional region, and I have a shape. So here's my blob shape. And I want to talk about the moment. Well, I have a piece. So here's my little piece, and I can talk about the mass of that piece. That's the density times delta A. But now, what moments could I have? Well, in 2 dimensions, the moments we typically talk about are with respect to the axes. So I have the x-axis, and I have the y-axis. And so I can ask, what's the moment with respect to the x-axis, and what's the moment with respect to the y-axis? And the thing that we have to figure out, the real part that changes with the moment problems, are what's your distance. So if I want to know my distance to the x-axis, what is my distance to the x-axis? If I'm at a point x comma y, how far am I from the x-axis? Well, I'm asking the question. No. Okay, you're right, it's y. So this leads us to the sort of the strange counterintuitive notation that throws people off. So when we talk about the moment with the x-axis, we denote it by the m sub x. The x there is an indication of where am I going in relationship to. So you have to specify an object. So here, the x is the x-axis. Now the distance function turns out to be y. So the reason why I say this throws a lot of people off is they say, if there's an x there, shouldn't be there an x in there. But that's not what's happening. The x in the m sub x is indicating what's the object you're taking the moment with respect to. And then here, this y is the distance. And similarly, of course, you could do it with respect to the y-axis. And in that case, your distance is going to be x. So be careful here. The subscript does not have to match what's on the inside. The subscript says, where are you going with respect to? And once you understand that, it makes more sense. Now, that's 2 dimensions. What about 3 dimensions? Well, we should do that. So if I'm in 3 dimensions, let's do a quick sketch. Here I am in 3 dimensions. I have my shape, but I'll just say, okay, here's my point. So I have a point x, y, z. What are some things I might want to do it with respect to? Well, in 2 dimensions, we did it with respect to axes, x-axis and the y-axis. In 3 dimensions, we say, it's not the axes, it's the planes. So, for example, down here, I have the xy plane. Now, if I want to know the distance to the xy plane, how do I find that? So if I'm at the point x, y, z, how far am I from the xy plane? Yeah, you're z. See, what happens is you just drop straight down. So that this distance here is z. Now, what if, say, I'm not in the xy plane? Maybe I am over here. All right, so I'm on that side. Okay, what plane is this? Yeah, it's the xz, because x comes forward, and z comes up. This is the xz plane. How far am I from the xz plane? We're y. And then, of course, one last plane, which hard to sketch, but okay, there we go. That's close enough. We have the the yz plane, and where do we get to? We drop straight back, and we get distance x, and that's to the yz plane. All right. Well, now that we understand that, it's easy to talk about the moments. So when we talk about moments in 3 dimensions, we talk about moments with respect to planes. So the xy notation here in the subscript, that's the moment with respect to the xy plane. And if I want to know the formula, I just say, what's the distance? And the answer is, it's z. So once you get this idea in place, okay, a moment is with respect to something, what's the appropriate distance expression? All these equations sort of fall into place. And in particular, instead of having to memorize 5 different formulas, you just say, okay, there's this generic framework, and how do I know how to apply the general framework? So it's really much more useful to be able to say, okay, what's the framework, and how do I apply it? All right. Any questions about computing the moments? Okay. Well, next thing is, what do we do with these moments? So that brings us to our center of mass. So what is a center of mass? One way to think about center of mass is you can think about is where's your balancing point? So if I had a 2-dimensional object, so in other words, a flat thing, the center of mass is where you could put your finger or some other pointing technology, and it would balance. So it would stay just upright. Whereas if you moved your balancing point over, it would tip. So the center of mass, that's one way to think of it. It's the point where everything balances. But I like to think of it in a slightly different way. Namely, I like to think of the center of mass as being a weighted average. So what I'm going to do is I'm going to average where the locations of things are. But I'm going to say that some locations are more important than others because there's more weight. So they should be counted as more. So let's visualize this with a really simple example. So suppose I have 3 weights, and they happen to weigh 3, 2, and 9. So the numbers 3, 2, and 9 inside the boxes are how heavy the things are. And they're located along an axis at locations 0, 4, and 10. And I'm trying to find where's the center of mass. Now, if we think about it as an average, we could say, well, one way we could average is we could just say it's 0, 4, and 10. We add those numbers up, 14, divide by 3. That would be about what? 4 2/3? Be roughly right around here. So that's if we just weighted the numbers and just said, look, 0, 4, and 10 are equally important. However, looking at this, you could say, well, why should they be equally important? There's a lot more hanging out at location 10. Shouldn't that matter more? And the answer is yes. So how are we going to do this? Well, let me just change it to a little bit different setting. Suppose these aren't actually weights. Let's turn to something you might be familiar with. Think of these as quiz scores. Now you're probably thinking, that's not realistic. Too many people got 10. But for a moment, let's just think of them as quiz scores. We could say, look, 9 people got a score of 10. 2 people got a score of 4, and 3 people got a score of 0. And I ask, what's the average of the quizzes? What's the average score? Well, you could say, well, I'd add up 10 9 times. I'd add up 4 2 times, and I'd add up 0 3 times. That would be the sum of all the scores. And then I divide by how many total quizzes there were, which is 9 plus 2 plus 3. Now, what are you doing here? Well, what you're doing here is when you add up the score of 10 9 times, you can think of it in a slightly different way. You can say, look, I'm going to add up to the contribution is the value 10 times 9. So it's a combination of two things. It's how many there are with where you are. So what's happening is it's 10 times 9, 4 times 2, 0 times 3. So it's a combination of location and mass. And then you're dividing by the total mass. So we're weighting these locations, 0, 4, and 10, corresponding to how much is actually there. And now if you carry out that computation, you'll see that it's not the same value we talked about a little while ago. It's, well, 0 plus 8 plus 90 is 98, and 3 plus 2 plus 9 is 14, which gives us 7, which means that under this convention, the center of mass is halfway in between 4 and 10. So there's our center of mass. All right. So again, we're somewhat averaging our locations based upon how much weight there is at that location. So that's our center of mass. That's the convention. Now, how do we go about computing it? Well, for a two-dimensional region, let's just go through and do one computation, and then we'll say, aha, in general, that works for everything, because it's the same idea for everywhere. So what does the computation say? I want to somehow average the x locations of my pieces, and how much weight does each piece get? Well, the weight of the piece is how much mass is at that location. So I break things up into pieces, and I say, okay, it's the x value times the density times the area. So in other words, it's location times mass. And now I'm going to divide by the sum of the masses. So I'm averaging the x values with this weighting, where the weighting is based on how much mass there is. Now we take the limit. It becomes an integral. So what does the top become? Well, the summation becomes integral. Then we have the x times your density dA. And downstairs, the summations become the integral density dA. And we say, well, have we seen these before? And hopefully the answer is yes, because it is yes. We have seen these before. Do you recognize the bottom? We'll start with that one. That one's probably more familiar. Add up the densities times the areas. What do you end up getting? Getting mass. And now, upstairs, we're adding up the density, and now we can think of x as a distance. So what do we have? We have a moment, and as someone pointed out, my. The moment with respect to the y-axis. So I can find the x location by taking a moment divided by the mass. Of course, similar idea works for the y location. So for 2 dimensions, I can find my center of mass by finding my moments and then dividing by the masses. Again, this comes down to just saying, let's reweigh everything. Let's take that weighted average. Now that's for 2 dimensions. What about 3 dimensions? The answer is, same idea. You just take those moments. Because what ends up happening in 3 dimensions is essentially, if you come over here, you just get an extra sum. And it's a delta V. Well, that's pretty much it. It's the same ideas. And so you get the moment with respect to the yz plane divided by m, and the moment with respect to the xz plane divided by m, and the moment with respect to the xy plane divided by m. But really what's happening is that these are basically the integral downstairs is the integrate density. The integral upstairs, it's either x times density, y times density, or z times density. You take those ratios, and you're good. Okay, so that's how you compute center of mass. Now you can imagine that this makes center of mass problems a little challenging. Because if I have a 3-dimensional object and I want to find center of mass, how many integrals do I have to do? You have to do 4. Because then the good news, you get to repeat this, you get mass for free twice, because it's the same value. But you have to compute the mass in 3 different moments. That's a lot of work. So we'd like to save ourselves some work. And it turns out we can. So there's a nice useful fact, which is the following. The center of mass will always lie on any line or any plane, if I'm in 3 dimension, of symmetry. Now, so that says, if you have a shape, and that shape has symmetry, you can cut your work down. Now, we have to be careful. What do we mean by symmetry? So there's a couple kinds of symmetry that are involved. So first off, there's the symmetry of the shape. And that is to say, if I flipped it across the line, or I flipped it across the plane, I'd get the same thing back again. But there's a second type of symmetry, which is the symmetry of your density. Which means, look, when I flip it across the line, I'm back to the same thing I started with. Both shape and density. So let's do a quick example. Let's identify any line of symmetry for the unit circle, and where the density is 1 plus x. So the unit circle is a very simple shape. It's a circle. Now, one thing we know about circles is circles have lots of symmetry in the shape. And by that, what do we mean? You mean it doesn't matter which line you draw, as long as you go through the origin, you can get any symmetry. So in other words, as I flip the shape across, I'm always going to get the same circle back, as long as I went through the origin. So there's plenty of symmetry to go around. Now the question is, are they symmetry, or what is the ones which have that symmetry also with respect to our density? So we have to distinguish. So there is lots of symmetry with respect to the shape. But what's something where we keep the density the same? Well, let's think about our density. Our density depends on 1 plus x. What does that mean? Well, it means if we were to come in and starting to shade, where's a part of our circle which is, say, very undense? In other words, density is low. The left side would be very undense, because on the left side, we have 1 plus x, and x is very small on the left. In fact, very, very small, because on the unit circle, x would go between -1 and 1. So it would be practically weightless on the left-hand side. Where is a part of the circle where it's very dense? Lots of density. The right-hand side. Because on the right-hand side, I have that x is 2. X is 1, so I get density is 2. So if you were sort of to lightly shade, what we see? Well, it's not very dense here, but then it starts getting more and more dense until you get over here. So if we were thinking about it in terms of a density, we see, okay, we have to be careful. Well, where is a line of symmetry that preserves both the shape and the density? The x-axis. So here, this is a line of symmetry which respects both density and shape. And pretty much every other line, the problem is you don't have that symmetry where you preserve x. When I flip across here, what happens is the x stays the same, because I'm doing more or less a change the y value. If I tried to go across a different line, so if I put a line here, and I said, okay, flip this way, you'll notice what happens is that the density has changed. So that it's now very dense here and very undense there. That's not the same. It changed. So therefore, it's not a line of symmetry. As a consequence of this, we say, okay, if we're computing the center of mass for this shape, what can I conclude? Well, the center of mass has to lie on this line. So my center of mass is somewhere on this line. What does that tell me about my center of mass? It tells me that the y-coordinate is 0, because all the points on this line have y-coordinate of 0. So without doing any integration at all, but rather just saying, tell me about the shape, I can conclude, aha, I know what the y-coordinate is for the center of mass. That saved me work. And saving work is very useful. Okay, well, let's try another problem. Okay. Find the center of mass for the region y squared less than or equal to x less than or equal to 1, where the density function delta xy equals xy squared. Okay. Now, this looks a little familiar, as if we've seen a problem somewhat like this before. Have we seen a problem like this before? Well, it looks a lot like this problem where we're finding the mass. So the good news is we actually have a little bit of work here already done. We can just copy it and we can say, all right, so we'll make some notes here. Whoop. Make some notes. So we're going to have our shape is still the same. So we'll just copy that. Here we have x equals 1. Here we have x equals y squared. We're going to shade in our region. And there's that. And we know our mass is 4 over 21. Because that's what it says right here. Okay, and we can also refer to this for our bounds. But for the time being, okay, that's what we already know. Now, we want the center of mass. Before we begin, is there anything that can save us some work? So, in other words, does this shape have any symmetry? I suspect it does. I mean, I asked the question. I strongly suspect it does. What symmetry does it have? Along the x-axis. This is a line of symmetry. Now, it's not enough, of course, just to say, oh, the shape is symmetric. You always have to double check and say, what about the density? And in our case, we can see that the density is also symmetric in the following sense. If I flip across, what happens is my x-coordinate stays the same, but my y-coordinate changes sign. Because my density has a y squared, changing sign doesn't change anything, because the square part fixes that. So this is a line of symmetry. So what can we conclude? Well, we can conclude y bar equals 0. Because on that line, my y-coordinate is always 0. So I find my line of symmetry. I'm halfway done. Amazing! Amazing! We're halfway done. And it feels like we've hardly done any calculus at all. My favorite type of problem. Okay, but we're not 100% done. So we still have to find the x-coordinate, and unfortunately there's not another line of symmetry available to us. So what's left for us to compute? I'll give you a moment to think about it. It's the moment with respect to the y-axis. But really the key here is that what we're integrating is we're integrating over our region x, which is our distance, and then times our density xy squared, which is our density. All right, so if we go back to the integral that we had on our last problem, we'll see it's pretty much the same integral. The only thing that changed is we have an extra x in there. So I can just copy down from last time. So this is the integral from -1 to 1, integral y squared to 1 of x squared y squared dx dy. And away we go. All right. So this becomes the integral -1 to 1 of 1/3 x cubed, evaluated from x equals y squared to x equals 1. Of course, there's also y squared there. I should also write down. I can write down afterwards because I'm just integrating the x part. So this will become the integral -1 to 1 of 1/3 y squared, and then I'm going to have y squared cubed, that's y to the 6, times another y squared gives me y to the 8th dy. So integrating, and hopefully this time I remember to actually put the right terms down. 1/9 y cubed minus 1/27 y to the 9th, evaluated from -1 to 1. That's 1/9 minus 1/27, subtract -1/9 plus 1/27. I should point out here that we could have saved ourselves some work. We could actually just say, notice that this function is even, because they both have even powers. It's y squared and y to the 8th. And so if I'm integrating from -1 to 1 of an even function, I could just have integrated from 0 to 1 and doubled the answer. But that's all right. We like work sometimes. All right. So rounding the corner, that's going to become 2/9 minus 2/27. Well, common denominator there is 27. So that gets 6/27 minus 2/27 gives us 4/27. Now, is this the right x-coordinate? No, it's not. That's the right moment. To get the right x-coordinate, what do? Well, x bar, it's the moment with respect to y over the mass. So that becomes 4/27, which is the moment, divided by 4/21. Well, the 4's cancel. This becomes 21/27. And now, what happens? They're both multiples of 3. And so this becomes 7/9. All right. So where's the final answer? Well, we now have the x-coordinate for the center of mass, 7/9. We already had the y-coordinate, so the center of mass is at 7/9, 0. Well, is this answer reasonable? So where is 7/9? 7/9, 0, we put it close to here. Now, what do I mean by reasonable? Suppose you computed the center of mass and you had ended up over here. Would that be a reasonable answer? No, very unreasonable, because the center of mass should be kind of center. Similarly, of course, if you had gotten a negative answer, definitely very, very unreasonable. But the other thing is to say, okay, look, there's a lot more shape to the right than there is to the left, so we would say we should be biased. We should be closer to 1 than we are to 0. So it's a reasonable answer. All right. I'll skip that one for a moment because there's one other topic to talk about. We've had one moment, but why not a second moment? And the answer is, you can have a second moment. In fact, it turns out you can have as many moments as you want. But the second moment has a name, and that's called the inertia. And what is the inertia? Well, it's a measurement of the tendency of an object to stay in its current state. So what's the inertia? We want to just say, look, what's your current state, and how hard would it be for us to get you to change? And how is it computed? Well, you'll notice it's called a second moment. And essentially, inertia looks a lot like a moment, except instead of looking at distance, it's distance squared. And that's it. Once you understand that, everything else falls into place. So what you do is you just go back through your old formulas and say, well, everywhere where I had a distance in my moment, now I'm going to put distance squared, and I'll get inertia. So we're only going to talk about inertia for two-dimensional objects, and we're going to talk about 3 of them. So we have the inertia with respect to the x-axis, which the distance is y, so it's y squared. The inertia with respect to the y-axis, the distance is x, so you get x squared. And then you have the inertia with respect to the origin. And that has a distance with respect to the origin is the square root of x squared plus y squared. So it might seem a little strange to talk about that. Sort of do a quick sketch of a picture. So here I am in the plane, and I can talk about various things. So here's a little tiny point of maybe a bigger shape, and I want to say, well, what's the inertia? What's the contribution of that part? Well, if you know your x coordinate and your y coordinate, so that's y, and that's x, then the distance from your point to the origin is the square root of x squared plus y squared. Now, you might notice, why is there a z there? Well, one way you can think about it is if we were thinking of this as the xy plane in a three-dimensional setting, the z-axis would be right here. It would be going into that piece of paper. So that's why it's called I sub z. It's the inertia with respect to the origin, or sometimes it's referred to as inertia with respect to the z-axis. Now the nice thing is, the square root is usually a pain, but now, because we squared it, it becomes just x squared plus y squared. And you could actually break this into parts, because you can distribute. So it's x squared times density times your dA. Well, that's your inertia with respect to y. And it's y squared times density times dA. That's your inertia with respect to x. Well, let's do an example. Find the inertia with respect to z, where r is the portion of the unit circle in the first quadrant, and the density is equal to x. All right, so let's try this. So I have the unit circle. I'm in the first quadrant. So here I am. So there's my shape. I'll shade it in. All right, so now I have r. So there is r. And I want to find my inertia with respect to z. So I come into here and say that my inertia with respect to z is the integral over the region of x squared plus y squared times my density dA. All right. But we were asked not just to write down the formula, we were asked to find it. We want a number. So how would we go about integrating something like this? Polar. This is highly suggestive of doing the problem in polar. Now, why is it highly suggestive? What are some polar suggestions this problem is making to us? Yeah, x squared plus y squared is definitely very polar-like. So when you see something like that, it's a very natural thing that says r squared. What are some other things that suggest polar? The region. This is a beautiful region in terms of polar. How can we describe this region? Yeah, theta goes between 0 and pi over 2, and r goes between 0 to 1. So that's good. The dA, what will that become? R dr d theta. And there's one little piece left. What do you do with the x? R cosine theta. So now we have all the pieces together. So this becomes integral r squared times r to the fourth. Cosine theta, dr d theta. Well, theta goes between 0 and pi halves, and r goes between 0 and 1. Well, because the bounds are so nice, and our function is so nice, you can actually compute this by breaking it up into two parts. 0 to pi halves, cosine theta d theta, and integral 0 to 1 r to the fourth dr. What's the integral of cosine? Sine. Evaluate it from 0 to pi halves. Sine of pi halves? 1. Sine of 0? 0. So this turns out to be 0. Oh, sorry, 1 minus 0, which is 1. Well, I was nervous for a second there. All right, integral of r to the fourth? 1/5 r to the fifth. And then we're going to go from 0 to 1, which becomes 1/5. 1 times 1/5 gives us our final answer of 1/5. 1/5. That's it. Now you might say 1/5 what? Well, if you're not sure what the units are, just think about what we added. It's the square of the distance, density, and of course I should have said a little bit of area here. So it's distance squared times mass. So maybe like kilograms times meters squared. Well, it's been a pretty packed week, so we didn't have time to get through everything in class, so I want to do a few more examples. We've done the theory, but the more practice, the better. So let's do some more practice. All right, rewriting the order of integration problem. So we have this integral, which is given to us in the order dy, dz, dx. So if I were working through this onion, first I'd integrate with respect to y, then z, then x. And the goal is we want to change the order of integration dx, dy, dz. All right, well, so what do we do? Let's start by figuring out what we're integrating over. So we're coming to our integral, we're going to figure out our bounds. So we work from the outside in to understand things. So the outer integral is attached to the x. So this -2 to 2 really means from x is -2 up to x is +2. So x is going between -2 and 2. Now once we get to the second layer, and that's the next one, that's with z, things get more interesting. So I'm going from z equals 0 to z equals 4 minus x squared. So 0 less than or equal to z less than or equal to 4 minus x squared. Now if we put these two things together, what are we doing? Well, we're in the xz plane, because there's just right now x and z. So we can sketch the xz plane, and we see that x will go from -2 to +2, and that z will go from 0, so z equals 0 is the down part, up to 4 minus x squared. Well, that is an upside down parabola, which conveniently happens to pass through -2 and 2. So currently, if we just go through only these two layers, we have this region right here. Okay, now to add on our third layer, our inner integral. So these are surfaces. So y equals 0 up to y equals 4 minus z. Now note that this here, y equals 0, that's very convenient for us because that really is the xz plane. And part of our building up, we said, hey, we're looking at x and z. So this is really nice because it's going to be the back part of our surface. All right, so let's see if we can't get a sketch going. So I'm going to draw a set of axes here. X, Y, and Z. So what do I look like? Well, I know the following. I know that I have this shape here. So I'm going from -2 to, positive 2, negative 2 back here. So -2 to positive 2, that's here. Up here is 4, so this parabola is here. So we're going to just sort of lightly sketch that in. All right, and that's what's happening here. And now in the y direction, we're coming from the xz plane. So this is the back half, and we're going to move forward in that direction until we hit the plane y equals 4 minus z. Well, what does that look like? Well, if we were just to sketch in the y-z plane, what does 4 minus z look like? It looks like a line. It intersects here at 4, actually intersects down there at 4 as well. So what I see here is I see, well, there will be a line coming down. All right. Now, what's the surface though? The surface is a plane. So in three-dimensional space, when I talk about y equals 4 minus z, I'm going to be seeing this plane here. So what's going to happen is I have this parabola shape, and I'm going to slice it with a plane. All right. Well, what's going to be the result? Well, what's going to happen is we're going to do the following. All right. So we have our parabola shape, and we're going to the front. All right. So, well, it's a little bit, have to think about it here. So we come down, and what do we have? So what we have here, this is the 4 minus z. So what's going to end up happening is it's going to end up, when we do the intersection, to look like this. So that this here, this slanted face, this is the face y equals 4 minus z. All right. And in some sense, it's kind of a doorstop shape. So there's a little bit of a curve on this side. Similarly, there's a little bit of curve back here, which we can't see very well on the back side, and so forth and so on. All right. So that's the first step. What's our region? Well, there we go. There's our region. There's our picture. Okay. Now we're ready to sort of tackle the next part, which is let's try to understand the new bounds. So we're going to end up with an integral f x y z dx dy dz. All right, well the dx, that's the last thing I need to worry about. So I'm going to look down the x-axis to begin with, because I like to set the bounds from the outside in. All right, so if I'm setting my bounds from the outside in, what do I see? Well, I'm looking down the x-axis, and what I'm going to see is I'm only going to see things in the yz plane. And in particular, the yz plane that I'm going to see is this shape. It's a triangle. So we're going to see this triangle here. So that is our shape. So looking down the x-axis, we see the following in the yz plane. We intersect at 4 and at 4. Now you might say, where does that fit in our picture? Well, essentially what we're seeing is we're seeing the side here. Because this plane y equals 4 minus z just becomes a line. And so what we're catching is we're catching that side from an angle. All right, okay, so we're in business. We're almost there. Here we go. We can see now, where does z go from? Lowest value of z is 0. Highest value of z is 4. 0 to 4. Now, suppose I fix a value of z. I'm going to go between two surfaces. And where are they? Well, I'm going to go from my left surface, which is y equals 0, to my right surface, which I need to have y equals, well, I already have it. It was given. That's the surface y equals 4 minus z. So I'm going to go to 0 up to 4 minus z. Now, we're getting close. Where are we? Well, we got to now figure out where are we in the picture. So I'm here, this doorstop shape, and I want to say, where will my values for x range between? What are my surfaces? So if I look, I can actually see what my surfaces will be, because what's happening is I'm going to be moving, let's mark it in the picture here, I'm going to move from this front, and I'm going to move in the x direction until I hit the back. So the front, where am I hitting? The front is this surface here, this curved surface. All right, where's the back? It's also the curved surface, it's the other side. So remember, where is this? It's coming from our parabola. That's where it's coming from. So I'm going from one side of the parabola to the other side of the parabola. Well, all right, what was that parabola? That was our parabola. That was coming from z equals 4 minus x squared. So I have z equals 4 minus x squared. Solve for x. X squared is 4 minus z, which means that x is plus or minus the square root of 4 minus z. Now we say, aha, plus or minus, so the front side, that's the square root of 4 minus z, and the back side, which we can't quite see, is negative the square root of 4 minus z. So I'm going to go from x equals minus square root of 4 minus z, because that's the lowest value. We go from low to high. So we're going in that direction. Low value to high value. Minus square root 4 minus z to plus square root 4 minus z. And we're done. Okay, done. Good, good. Now this one's a little more challenging. It requires a little bit of visualization, but it's practice. Draw your surfaces. What do you look like? What's the shape? Be careful. Look down your axes and one layer at a time. Okay, so that was a topic for Monday. Well, let's move on to a topic a little bit more recent. Okay, so suppose S is a solid below the plane z equals 2. Now that part, that's not too hard to understand. So if I'm drawing in my space here, z equals 2, what's happening is down here, the xy plane is z equals 0. So I'm up here, z equals 2. All right, so I'm below z equals 2, and I'm above a lot of other planes. Z equals 2x, z equals minus 2x, z equals 2y, z equals minus 2y. And there's a note, this looks like an upside down pyramid. Now, given the density function, delta of x, y, z is whatever, we'll get to that later, find the total mass. Now, it's not hard to find mass, you integrate density, so the hard part of this problem is going to be setting things up. So it's good to understand what things look like. So let's sort of take things and put them together. So what do we see? Well, we see the following. If we look at these pairs, we're above z equals 2x and we're above z equals negative 2x. What does that mean? Well, imagine for a second we were looking down the y-axis. So we were looking from this direction. So we only saw the xz plane. What would we see? Well, if we looked at these curves in the xz plane, z equals 2x, that's a line, and z equals minus 2x, it's another line, and I have to be above, which means that I'm going to end up being above these points. So if I were to look at this shape down, again, looking down the y-axis, I'd see this. Of course, I'm going to stop when I hit z equals 2, because I'm below z equals 2. Now, suppose I look down a different axis. Suppose I look down this way. So now I'm looking down the x-axis. Well, when I look down the x-axis, I see the yz plane. So I see z equals 2y, I see z equals minus 2y, and I'm above those, which means my shape is going to look like this. But then, of course, I stop at z equals 2. All right, so that's what I see when I look down one direction, and when I look down another direction. It's kind of like a cone. But a cone, see, it doesn't matter which side you look at, it's always going to be the same. Now here, this is not a cone, but what's going to end up happening is we're going to get the following. So it's an upside down pyramid. So I come up here to z equals 2. And what happens? Well, at 2, it's actually not too hard to see that I'm going to be between negative 1 and positive 1 for y, and similarly between negative 1 and positive 1 for x. So I'm going to have this square up here floating at z equals 2. All right. So there we go. And now what happens is looking on this direction means that the sides are going to come in. So I'm going to have these sides coming in, and similarly from the back side, similarly from over here. So that I see this upside down pyramid shape. And you can convince yourself, if I look down the x-axis, certainly the y-axis, or if I look down the x-axis, I'm going to see the right shape. All right, so that's our solid. Here is S. And we're going to try to understand S a little bit better. Now we need to find the integral. So our goal is to find the following integral. Mass is the integral over our solid of our density dV. So that's going to be the integral of our density, 9 plus arctangent. Oh, an arctangent problem. Okay, well, we'll get to it. We'll get to it. Y squared z. And we're integrating dx, dx, dy, dz. Now, we should stop for a second and think about the order here. Now, normally we say the natural order is to have the z be the innermost integral, because that's the one where we have surfaces as z equals. If you think about that, though, if you did that in that order, it would kind of be terrible. Why? Well, if you think about it in terms of how z varies, the challenge is that, well, actually, let's do it this way. Suppose you look from above. So down the z-axis, we'll draw ourselves a quick picture here. So if I was looking down the z-axis, what would I see? I'd see the xy plane, and I would see the top of my shape would just be a square. All right. It's a square that goes from negative 1 to positive 1 in both the x and the y direction. Now suppose we lift the square off. What do we see? And the answer is we would see 4 triangles. And each one of these triangles here corresponds to part of our surface. Now, as an example, if we label this here, x, y, and z, all right, this triangle right here, where does that fall? Well, that corresponds to this triangle right here. So let me shade that so we can follow it along. So this triangle here corresponds to that triangle there. Now, what's the thing here to notice? If we were going to integrate where z was on the inside, all right, the thing is, I would have to use one integral for that piece, because I have a surface on the bottom, that's this part of a plane, and then the square on the top. On the other hand, that's just part of it. And then I'd have to say, okay, what about the next piece? Well, okay, what is the next piece? Well, maybe we want this triangle here. Where is that? Well, that corresponds to this triangle, which we can barely see. In fact, we're kind of cheating a little bit, but there's a triangle right there. So again, it'd be a separate integral. So if we were going to integrate in the order dz, dy, dx, we'd have to do 1, 2, 3, 4 integrals. So sometimes dz, dy, dx is not the best. You always want to think, okay, what's a good order of integration? And you want to make sure that when you're looking at high value minus low value, that you always have a consistent high value and a consistent low value. When you have lots of varying low values or lots of varying high values, multiple integrals, and it's just another code word for more work. Well, we like work, but I don't know if we like that much work. All right, well, let's think about what's happening here. So if I'm doing the order dz, dy, dx as suggested, I'm going to look down the x-axis, which means my picture looks right now like this. Here is my picture. And I ask myself the question, okay, where does z go between? Well, I go from 0 to 2. That's not hard. Usually the outer integral is not the hard one. Now I say, all right, what's next? I want to know where y goes between. Well, what do I have? I have that this is the surface, z equals, what is that, 2y, and this other one, z equals negative 2y. So because I have those, I can now say, all right, I'll take those two and I'll solve. So the one on the right-hand side will become y equals 1/2 z. And why am I solving for y? Well, this integral here is a dy integral. So I want to go from y equals to y equals. So 1/2 z, and this other side here, that'd be y equals minus 1/2 z. So minus 1/2 z to plus 1/2 z. Okay, so that's the y integral. Now we go to our last integral, our inside integral. And we have to say, okay, we got to figure out what is that integral doing? Well, what's happening? Now what's happening is I want to look at the full picture. I want to say, well, where does x go between? So I'm letting x move back and forth. So I'm going to go in between two of these planes. There's this front triangular plane and this back triangular plane. So what are those two planes? Well, the front triangular plane, that would be the plane z equals 2x. And the back triangular plane, that would be what? Well, that would be z equals minus 2x. So, similarly as before, we want to go from an x equals to an x equals. So we solve for x equals minus 1/2 z. Here, we get x equals 1/2 z. And so our bounds are minus 1/2 z to plus 1/2 z. All right. Good. We figured out our bounds. We've got our picture. And now we're ready to integrate. So that's our next step. Let's actually integrate. All right. So let's see. What's our first integral? Ooh. First one right off the bat. Arctangent of x to the fifth. Now, arctangent of x to the fifth looks like a really strange function. And to be honest with you, the first reaction is, I don't think I want to integrate that. And that is a very reasonable reaction. In fact, I would say it's probably an appropriate reaction. We don't want to integrate arctangent of x to the fifth. Now the 9, no problem, we can do that. Well, if we stare at this for a minute, though, we say, okay, it's a very strange function. It's a very peculiar function, unusual, weird. And some people might even say that arctangent of x to the fifth is odd. This is an odd function. Now, why do we note that? Well, look at our bounds. We're going from negative 1/2 z to positive 1/2 z. See, we're going from negative to the positive, which means we're going straight across, equal amounts on both sides. When you integrate an odd function from negative something to positive something, what happens is that the cancellation occurs. So that part goes to 0. Gone. Gone. Now, the other part, I'm integrating from negative half z to positive half z of 9. Well, that's not bad. So what do I get? I'm going to get integral 0 to 2, integral negative 1/2 z to positive 1/2 z of 9x y squared z, evaluated from x equals minus 1/2 z to plus 1/2 z. And then we have dy dz. Now when you plug it in, you're going to get a 9/2 z, and then you're going to subtract negative 9/2 z, which means when you put those two together, it becomes 9z. So this becomes the integral 0 to 2, integral negative 1/2 z to plus 1/2 z, and we said it's going to become 9z, and so we're going to get 9y squared z squared dy dz. All right, well, this becomes integral 0 to 2, and now we integrate with respect to y. We're going to get 3y cubed z squared evaluated from negative 1/2 z to positive 1/2 z and dz. I should say these are y equals. All right, y equals dz. Well, okay, what happens here? Well, 1/2 cubed is going to become 1/8. And so what we're going to get is this is going to be the integral 0 to 2. All right, we're going to get 3 times 1/2 cubed, that's 3/8. And then we have z cubed and z squared, which will become, should become 3 z to the 5th. Now you might say, whoops, you made a mistake. You said 3/8, but you wrote 3/4. Well, we're going to get positive 3/8 when we plug in a half z, but then we're going to subtract negative 3/8 when we plug in negative a half z, and that combines to give us 3/4. All right, dz. All right, we're getting to the end of the paper, but also the end of the problem. So this is going to be integrate 3/4 z to the 5th. This is 3/24 z to the 6th, evaluated from 0 to 2. Now 3 over 24, that's the same as 1 over 8. 2 to the 6 is 64. And of course 0 to the 6 is 0. So you get 1/8 times 64. Final answer is 8. And that's it. Done. Okay, now what happened in this problem? So this is an interesting problem. There's a few things that happen. It's good to try to understand the shape, which came from saying, okay, we have a bunch of surfaces coming together. And in this case, it gave us the order of integration. But one of the things is we should know that we should not try to choose an order of integration that involves many integrals. So that really rules out having dz be the inner integral. Now, in some sense, the interesting part was that there was this red herring, this arctangent of x to the 5th. And really, ultimately, what allowed us to get away without having to integrate it was symmetry. Now, in this case, what happened was that there was some symmetry, and it was across this direction. So if I look at where I have a positive x, there was a little bit over here on the negative x side where I could actually get some cancellation happening. So look for symmetry. Symmetry is a very useful tool in mathematics and simplifies lots and lots of problems. All right, I think we have one more problem. Okay, last problem. So we found a mass. Now we're going to find a center of mass. So find the center of mass for the solid, -1 less than or equal to x less than or equal to 1, -y less than or equal to, -1 less than or equal to y less than or equal to 1, and 0 less than or equal to z less than or equal to 2. And our density is x squared z plus y squared z squared. Now, this is three-dimensional, but it's actually a pretty simple three-dimensional shape. If we were to sketch this, what do we have? X is going from +1 to -1. Y is going from +1 to negative 1. So we get down here a nice square and negative 1. And then z goes from 0 up to 2. So our shape is going to be this kind of shape. So our region is a cube. And the nice thing about cubes is they have lots of symmetry. So given that our region is a cube, we'd like to sit down and say, okay, our region is a cube. What symmetries do we have? Well, there's a couple of natural, obvious symmetries to look at. So let's point some of these out. All right, here we go. Let's see if this will mark. So here I'm going to look at the following one. Now, this is a plane, and in particular, which plane is it? This is the plane y equals 0. All right. So if I look at this symmetry here, the question is my region symmetric? And it is, because there's this one half of the cube and it flips the other half of the cube and vice versa. Now the question is, what happens if I flip across? What happens to my density? So in other words, if I'm here and I have a density and then I go flip through that plane, is my density the same? So, all right, well, what happens? Flipping through the plane is the same as saying going from a positive value y to a negative value y. Now notice, the only place where y shows up is it's something which is squared. And because of that, we say, look, whether you're at the positive side or the negative side, you have the same density. So in other words, you have the same density on both sides. Now, that tells me something. What it tells me is that when I'm looking for my center of mass, it has to be on that plane. It's on the plane y equals 0. All right, let's try another center of mass. Or sorry, excuse me, another plane. So we're going to take now, instead of y equals 0, what if we tried this one, which is the x equals 0? What can we say? Well, similar idea. If I think about flipping across the plane, it says, well, if I have an x value, swing it over to negative x. And I look and see, the only time x shows up is it's squared. It has no effect on density, which means that I see the same density on both sides. So that means I'm also on the line x equals 0. So combining all that information together, I said the line, I meant the plane. If I'm on the plane y equals 0 and I'm on the plane x equals 0, I have to be on the intersection, which is here. Okay, so I now know that my center of mass is somewhere on the z-axis. It's somewhere on the z-axis between z equals 0 and z equals 2. Now there's one more potential symmetry we should check. Now the last potential symmetry we should check is, what about the cube if I go halfway around? So here I cut my cube in half. So here is z equals 1. Now if you look at the shape, it's symmetrical. So in other words, there's the same shape below this as there is above it. But is it a symmetry point? Because if it is, then we're really done. And the answer is no, it's not. You can check it because, for example, say I'm here at this corner. Well, that's x equals 1, y equals 1, z equals 0, which would be a density of 0 because I get 1 times 0 plus 1 times 0. If I flip across, I'm up here in this corner. What's my density? Well, it's 1 times 2 plus 1 times 4, which would be not 0, it's 6. So the density doesn't get preserved when I flip across z equals 1. So this is not a line of symmetry, which means we have to do more work. Okay. The good news is we don't have to do a lot of work, though. We've already established, by what we just talked about, we now know for sure that x bar and y bar are 0. Good. Well, what's next? We need z bar. If we need z bar, it means we need two things. We need the mass and the right moment. So let's do the mass first. The mass is going to be the integral, and it's negative 1 to 1, negative 1 to 1, 0 to 2 of the density. So x squared z plus y squared z squared. And we did this in the order dz, dy, dx. Cubes are very easy to set up for integration. All right, how do we do this? Well, probably the easiest thing to do is say, you know, we could really think of this as two separate integrals, -1 to 1, -1 to 1, 0 to 2, of x squared z, dz, dy, dx, plus, similar thing, -1 to 1, -1 to 1, 0 to 2, of y squared z squared, dz, dy, dx. Now, why do I say that? Well, these integrals, because the functions are very simple, the bounds are very simple, we can just pull them apart. So this becomes integral -1 to +1. I'll work on the x term. So x squared dx. Then I'll go to the y one. -1 to +1. There's no y, so it's just dy. And integral 0 to 2 of z dz, plus similar thing over here, -1 to 1, and then it's going to be just dx. There's no x term in this part. Integral -1 to 1 y squared dy, and integral 0 to 2 of z squared dz. All right, well, here we go. This is 1/3 x cubed from -1 to +1. This is 2. Well, because you're just integrating 1 from -1 to +1, so it's the length. This is 1/2 z squared from 0 to 2. Plus, all right, this integral 2. This integral 1/3 y cubed, -1 to +1. Plus, here, oops, that's not a plus, that's a times. Times. Sorry about that. Forgot. My apologies. Okay, times 1/3 z cubed from 0 to 2. And 1/3 times 1, subtract 1/3 times -1 cubed, which becomes 1/3, well, minus a third. So this is 2/3. This will be 2. 2 squared was 4 times a half is 2. Plus 2, similarly, before that's 2/3, becomes 1/3, subtract -1/3, and this will be 8/3. So what do we have? We have 8/3 plus 8 times 2 times 2, that's, well, that's 32. 32/3. And 8/3 plus 32/3 is 40/3. So there it is. Now, is that our answer? No. Impossible. Impossible. Why? Well, just look at it. That's 40/3 would be way up here. If it was a value for a location, that's obviously not right. And that's not what we found. What did we find? Well, we work our way back. M. That's our mass. So that's not a coordinate. That's just the, well, it's part of our coordinate, but that's not the whole coordinate. Okay, so now we know M. M should be 40/3. Well, it's not enough. It's not enough. We also need to find our moment. Well, which moment? Okay, so the moment that we need, because we're doing it, we're looking for a z bar, is we're looking for, when we do the integral, the only change would be we want to add a z. Now, we can either remember that that's what we're looking for, or we could be fancy and say that means that we're looking for the moment with respect to the xy plane, because the distance to the xy plane is z. All right, so we're going to find the moment with respect to the xy plane. So that's going to be integral -1 to 1, integral -1 to 1, integral 0 to 2 of, add the distance term, that's the z, x squared z plus y squared z squared dz, dy, dx. Now, at this point, we're just going to do a lot of the same process, so it's not going to be very exciting, but it's good practice. We're going to distribute the z through, and then we're going to break it into two integrals. So we're going to have -1 to 1, -1 to 1, 0 to 2, x squared z squared dz, dy, dx, plus integral negative 1 to 1, integral negative 1 to 1, integral 0 to 2 of y squared z cubed dz dy dx. In the interest of time, we'll again pull these integrals apart. So this will be integral negative 1 to 1 x squared dx, integral negative 1 to 1 dy, integral 0 to 2 of z squared dz, plus integral negative 1 to 1 dx, integral negative 1 to 1 y squared dy, and then integral 0 to 2 z cubed of dz. Now the good news is some of these integrals we already know. So we can actually just skip ahead, because the integral of negative 1 to 1 of x squared, we did that. That's positive 2/3. So this is 2/3. Negative 1 to 1 dy is still going to be 2. Integral 0 to 2 of z squared, well, that's one we actually did. Integral 0 to 2 of z squared was 8/3. So that one's one that we already know. This is also still 2. This is also still 2/3, which gets us to this integral here. So this one, well, that'll be 1/4 z to the 4th, evaluated from 0 to 2, and 1/4 times 2 to the 4th, that's 1/4 times 16, which is 4. So what do we have? We have 2/3 times 2 times 8/3, and that will give us a grand total of, and this is making me a little bit nervous here. Oh, I made a mistake. Let's go back and fix it. Well, we still have our minds here. I forgot to multiply the denominators down here. So it's 2 times 2/3 times 8/3. That's 32/9. Okay. All right. Which means what's our common denominator? Well, we want to get 9ths. So that's 24/9 plus 32/9, which would make it 56/9. Yes? Yes. 56/9. Okay, good. I got nervous here because I said, oh, wait a second, we're getting a 9th. I didn't remember that. It's always good. Now look, go back, fix your mistake. Find your mistakes and fix them. It's how you get better at doing math. It's how you get better at life. All right. 32/9. What do we have over here? 2 times 2/3 times 4. Well, that's going to be 16/3. So plus 16/3. All right, 32/9 plus 16/3. Now, what happens next? Well, we've got to get a common denominator. So that's going to be 32/9 plus 48/9, which gets us a grand total of 70. Oh, well, no, not 70, because that'd be 80/9. There we go. There we go. 80/9. All right. Well, now, is this our coordinate? The answer, no. No. But we're close. So the center of mass in the z direction is going to be the moment with respect to the xy plane divided by the mass, which is going to be 80/9 divided by the mass, which we wrote over here. That's 56/9. Now the nice thing is the over 9's cancel. So we get that this is 80 divided by 56. Now that seems like it probably could be made simpler. Let's see, do they have anything in common? Well, they both are divisible by 2. We could try that. So that's easy to spot. So that would be 40 divided by, here, let's see, if we divide this by 2, we'd get 28. All right. Oh, we could do even better. Those are both divisible by 2, so that's 20/14. And let's see, again, another 2, 10/7. 10/7. Okay, now that's clearly, we're not going to get better than that. All right. Well, so that says 10/7. Is that reasonable? Let's think back to our picture. Now, our picture says we're going in the z direction between 0 and 2. So z equals 0 to z equals 2. So 10/7 is between 0 and 2. It's a little bit higher. So 1 would be 7/7. So it's almost up to 1.5. So first off, it's in between 0 and 2. That's a promising sign. But it also says I should be biased towards the top. Now if you look at it, that makes sense. Look at what's happening here. As your z increases, your density increases. So it's more dense the higher up you go. So we should be biased towards the top. So that means 10/7 is a very good guess. It's probably even right, which means it's a great guess. But now let's put it all together. We already used symmetry to get our x and y, and then we did work to find our z. So our final answer is the center of mass is 0, 0, 10/7. Now, what do we learn? Well, be patient. Double check your work. And like here, whoops, that happens. Mistakes happen. Well, go back and fix them when you spot them. Certain things should be repeating over and over again. If you say, wait a second, this didn't quite feel like it's doing the right thing, you can fix it. And the sooner you fix your mistakes, the better. The other thing is just be patient. Yes, these problems take time, but there's a method to them. And just work through it a little bit at a time. We said, all right, take the integral, break it up, work each piece, see what's happening on each piece, and slowly but surely we get the answer. We find the right values. All right, that's it.